Alright, welcome back to MECH1340. We're moving right along in Chapter 2. We're just going to talk about the PLC hardware components. Alright, I'm going to go back and forth because we're using some of the Siemens 314s and then we have the Siemens 1500s as we're going back and forth through some of this. Okay, so just to recap, PLCs, programmable logic controllers, they're used in industry. Alright, we run all kinds of control systems off of them. We use it to control sequences, we use it to control automation, mathematical operations, all kinds of different things. And while we used a PLC, we wanted to replace hardwired relay control. So advantages, right? Eliminates the hardwiring. It's more reliable, low cost. Okay, it's flexible, fast response time, and it makes it a lot easier for us to troubleshoot. And we talked about all this in Chapter 1, so I'm not going to spend a ton of time on it, okay? But if we take a look at a PLC, right, has a couple different parts here, right? It's got its inputs and outputs, so that's what we're wiring to the field in, okay? And then we have our CPU unit, all right, our central processing unit. Each part of it has a memory and then a microprocessor. So remember, microprocessor, that's no different than what we use in class with the Arduino boards or Raspberry Pis or those sort of things, okay? So let's just talk about what kind of microprocessors are used in Siemens PLC, okay? They use Intel microprocessors, at least at the time when I'm doing your lecture here. All right, and then the microprocessors that are used in Allen Bradley are usually Motorola microprocessors. And again, this is at the time I'm doing your lecture, and they've been this way for the past few years, so things really haven't changed. Okay, so the I/O section, okay, that's where all the field devices are connected. So there's a slot here for inputs, a slot for outputs. All right, there's a slot for analog as well. So we have a DI slot, a DO slot for digital input, digital output. That's what those stand for. Okay. So pictured on the left, the darker one, that's our Siemens 314 PLCs that we have on some of the 870 stuff and some of the older ones that you're going to just be working with, just so that you understand how to do the architecture a little bit differently on the 314. And then the lighter colored PLC, those are the newer ones we have. Those are our Siemens 1500 PLCs. Okay, those ones quite expensive, but the same kind of operation, just more up to date for automation and being able to do stuff, networking and things like that for smart industry. That's really what the update is, kind of between the two. Those are more smart industry. Everything's going to kind of be tied together with an IPO address. Before, like the 314s, they had to use like Profibus, and everything was connected with this little purple cable and things like that. Okay, so if we take a look at the I/O section, all right, so if you take a look at the picture I have up here, and then you take a look back here on the previous slide, right, you can see on the left-hand side what we're referring to here is where the processor is located, okay? And then the rack goes on. Now what I'm showing here is our fixed I/O PLCs versus ones that are modular. The picture here is showing modular, okay? So the processor kind of connects to the side, and then we have the logic rack. So the logic rack is where we add all the different slots on. So like our troubleshooting PLC trainer, that one's modular. You can see where we have multiple I/O racks that are sitting there. All right, addressing. I'm not going to get into too much detail on this one. I'm going to cover this a lot more when we are programming. My addressing slide's here a little bit older because it shows the 314 and the 315 PLC, but I don't have the same addressing one for the 1500. But I do want you to know that the addressing for the Siemens is going to be the same. Okay, so I's are inputs, Q's are outputs, and how we actually write up the address, so like I 0.5 or Q 4.2, okay, still going to be the same thing. And then addressing just changes, right, as we add more modules on, more slots on, so that we can get more I/O on. It's really kind of how it goes. So well, they still use the I, IB, IW, ID kind of tag when we're adding more addresses. Okay, so that's really what it is on the left-hand side. If we take a look at that, for what we're doing in class, okay, at our level, we're not going to be going above 128 anyways. So we will be good. Okay, and then if it just needs to keep going, this is how we do the same exact thing with outputs. okay, and where the ranges can go when we go above 128. We're not going to do that. Some places you might work in industry. Just know that what the difference between like Q and QB is where the IO address slots are. So once you go above 128, we start changing the tag on the address. Okay. So how do we address and what it means and that sort of thing, we're going to get into this. So this is the 1500 that we're looking at here. All right, so most of us, we did this in digital electronics, but we know the smallest unit is a bit, okay, is a bit, and 1 byte is 8 bits. So when we transmit like an IO, right, we're going 0.0 up to 0.7. So we can transmit up to 1 byte. But each one of those is a bit, okay? Then a word is 2 bytes, okay? And a double word is 4 bytes, okay? A nibble is 4 bits as well. All right, so here's how we're going to address in Siemens, all right? So what really happens is we give the type, the slot, and then the word and the bit. Okay, so how that really works out here is the type, we have to define, is it an input or an output? Okay, so for Siemens, for input, we're going to use an I. For output, we're going to use a Q. So it's very important that you know that Q is an output, I is an input. The slot, that's the physical location, and we start at 0, and then we go 1, 2, 3, 4, 5, 6, 7, and count up. Okay, so the slot, in this case, it's 0. It's the closest one to the processor. Okay, and then the last piece is the bit. So that's going to be 0.0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, or 0.7. Okay, and then once we get to 0.7, then we start over and we go 1.0, 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7. Then we start over at 2.0, 2.1, so on and so forth. So that's how we're identifying this. So this example here is input 0.5. If it was an output, we would call it like Q5.0. So also, when we're addressing these, we give them a specific location. So I'm not going to call this, you can't call it input 4.0 and output 4.0. So you can't have a Q 4.0 and an I 4.0. All right, you're going to designate a certain amount of slots that go to inputs. Okay, so when we set up our programming, we're going to say, all right, 0 to 2 is going to be our inputs, 3 will be our analog, and then we're going to say 4 and 5 are our outputs. So they cannot share slot and bit, if that makes sense. So just to reiterate, I cannot have I 4.2 and I cannot have Q 4.2. They cannot share the same slot and bit. So that's why we designate a certain amount of numbers that are going to go to inputs and a certain amount that are going to go to outputs when we wire those in. Okay? So let's talk about the I/O section. We've been doing this in a lot of the classes, right? We've seen all these in the electrical class, even all the way back to digital electronics, all right? We have limit switches, read sensors, push buttons, ultrasonic sensors. All right, those are all getting tied into the inputs on our PLC. Or some things that we have on the outputs, right? We got our motor starter, our relays, our signal column, our cylinders. Okay, those are going to be tied more through solenoid valves, though, as far as how we're going to control those cylinders, because the cylinders are pneumatic, but we can control the solenoid valve that opens and closes the plunger that allows the air to flow one way or another through the control valve. All right, so that, kind of in a roundabout way, but we use the solenoid valves to control the directional control valves that control the cylinders. All right, so let's talk about different types of memory. Some of these you may or may not be familiar with, but when we talk about RAM, that's random access memory. It's fast, and you have to remember, always a test question, RAM is volatile. RAM is always volatile, okay, so it doesn't store. RAM is a working memory, so like when you need a good graphics card for gaming or things like that, you want to make sure that graphics card has a lot of RAM on it. Okay, if you don't have a lot of RAM, your game gets choppy and slow. It can't keep up with the software. Same with, if you have Windows. Windows 10, requires at least a minimum of like 8 gigabytes to work it. I think they tell you 4, But if you're only running 4 gigabytes of RAM, all right, things are moving very, very slowly for you. And if you have multiple programs open, all right, your computer starts to bog down. So it's your working memory so that you can have a whole bunch of things open or a bunch of processes going on at once. Okay. A ROM is a read-only memory. I don't know if you guys remember CDs or anything like that, where we would store everything on there. You couldn't rewrite over that one, but you'd come and use software. You know, some of you guys have video games, you buy discs. All right, those are more DVDs, but those are usually ROM, okay? You can only read what's on there. You can't overwrite those discs, all right? And then there's PROM, okay? Memory is non-erasable once it's programmed, okay? So PROM, so programmable read-only memory. So you can only write it once and then it sticks to. EPROM, that's erasable, so think of this like as a rewritable disk that you can use. It's erasable and using a strong UV radiation dose, okay? So you don't really want to be around that, but that's just kind of, you know, your ultraviolet light laser type scenario there. And then EEPROM, electronically erasable PROM. It can be erased while in the circuit, okay? So that's you overwriting something. So we use flash memory. It's non-volatile, all right? It has a high capacitor memory. So what is that? That's our little SD card that's going to be sitting inside our PLC. Same thing that you have like a thumb drive or things like that. Okay, so our programs, when we download them onto the PLC, they're going to go onto the flash memory. So they're going to go on a little card. So I could pop that card out, go to a different PLC, and put it in and be running the program that I have on that card. Okay, so load memory, okay, that's the flash memory. So this is what Siemens has been using since 2002. Our Fanics, some of them have cards in them as well, different types of things like that. Working memory, like I talked about, that's the RAM, okay? The random access, remember that one's volatile. So that's our working memory. So like I said, video cards, things like that. If you have, PowerPoint, SolidWorks, and Multisim like all pulled up and open at the same time, it allows you to move smoothly between those two. Just like, if we don't have enough RAM for SolidWorks, there's a huge lag in when you're drawing. So that's our working memory, that's RAM. Okay, and then system memory, okay, that's the one that stores the variables when you're running and executing a program. So it's just storing data as you're using it. Okay. The HMI, we have one of these on station 1, but we don't really interface with it much. You're going to do that in your level 2 stuff if you get there. All right, but that's just designed so that we can communicate with all the devices. Touch screen, right? We can monitor devices, change different things. Essentially, it's there to replace push buttons and switches and lights and things like that. But we can, override them in monitor systems. So, but more and more as we get into more smart automation, you're going to have more HMI to monitor systems and things like that. All right, so every Siemens PLC, all right, is going to have all these different pieces to them, right? We got a microprocessor, it's got to have RAM, it's got your SD card slot, a lithium battery if they're older. We don't have lithium batteries in ours. All right, MPI, that MPI connection is on our older ones. So what's shown in the picture here is one of our older PLCs. Those are the 314s, and we use an MPI. Okay, it's kind of a serial to USB to connect to our laptop. On our newer ones, on our 1500s, we're just using an Ethernet Cat5 cable to interface because everybody's got an IP address now instead. So we're not going to do too much with the MPI piece. The 315 lab, you'll use an MPI connector as well. And they used to use Profinet on a lot of these. That's a nice purple cable. We're not going to be using those anymore. Now that we can run and connect with IP addresses and Ethernet cables, okay? They're all going to have status indicators, all right? System fault, that's what the SF is, so something's, it had to halt in the middle of a program or things like that, or initial conditions aren't met, you'll see that fault set up there. All right, and then we got the run, and then we got the stop mode, and we have the mode selector, okay? So on the 314s, it's a little toggle switch. On the 1500s, it's actually a little LCD display screen that you got to go through. Okay, and we have our input-output modules. All right, those are all on our 314s and our 315s. We've kind of gone over that in our 1500s. Okay, other models, there's different ones for interface and communications and those sort of things. All right, so let's talk about real time. All right, so the definition, right? The system operates in real time when it reacts to an event that occurs on the field within a time constraint. All right, so let's talk about examples, right? So an airbag, right? If you get in an action, it has to respond to a collision in real time. So the second that your car detects some sort of collision, right, that airbag has to go off. All right, real-time tracking and surveillance, right? Cameras connected to the network. All right, processing to respond to events that take place. So if you got drones flying around and they need to react to what's going on the ground, all right, you need real time. You don't want like a 5-minute lag on the signal. Okay, so non-real time. Okay, we're offline in non-real time and we are online in real time. Okay, so if we're recording sonar scans or something like that, that's considered offline. All right, we don't necessarily need real time in that because we're not reacting to the situation. All right, so a mechatronic system does not respond in real time. What could be a possible description of this system? All right, so let's take a look. All right, so our answer choices here is it responds before the time is supposed to, it responds in the time after it's supposed to, it records data to be processed later by system components, or all of the above are possible. It is C, right? If it's not in real time, it's recording the data to be processed later by it. That's if it's not in real time. Okay, so binary, right? Why do we use binary? We've talked about this in digital electronics as well before, right? Binary is easy for us to code. Something is either on or off, and we can string a bunch of binary characters together. So we can string a bunch of zeros or a bunch of ones together to define a number or a word or a variable or things like that. So everything, even your keyboard, okay, goes down to the ASCII code and things like that. Each one of those is a binary string of numbers that produces a G or an H or a K on your keyboard and things like that. And just to reiterate, right, the smallest unit's the bit. The byte is 8 bits, okay? And we talk about a word is 2 bytes, a double word, all right, is 4 bytes, which is 32 bits. Okay, so how many bytes are there in a kilobyte? This is where we differ slightly, right? So I remember, like, kilo, the prefix is 1,000, all right? When we're talking our SI prefixes, it's a little bit different here in binary versus decimal. So to you and I, we have like a 1 kilo ohm resistor is a 1,000 ohm resistor, but in binary, a kilobyte's a little bit different the way it calculates. Okay, so a kilobyte is 2 to the 10th bytes, which is 1024 bytes. Okay, so when we talk about this in terms, don't think a kilobyte is not 1,000 bytes, it's 1024 bytes. Okay, so I just want you to think about that and know there's a difference between when we approach something as a decimal or approach something as a binary. Okay, so just think about that. So a gigabyte, is not an exact number like you think about. There was big lawsuits over hard drives and things like that about the actual true size of a hard drive. Okay, but if we look, decimal to you and I, a kilo is 1,000, a mega is 1,000,000, right? But for us, okay, in the binary world, a kilobyte is 1024, a megabyte is 1,048,576. So there's a big difference there between mega in our decimal SI prefix notation and our binary bit, all right, when we take a look at those. All right, and then lastly, how many bits are there in 2 kilobytes? All right, so we know a kilobyte is 1024, and we have to take 2 times that times 8, right? There's 2 kilobytes, so we're going to take 2 times 1024, and then we want it in bits, right? So we got to multiply that by 8. So there's 16,384 bits when we do that calculation. All right, so just remember, and we've covered this in digital electronics. I'm going to review a little bit more probably on the board or things like that. Decimal numbers, right? Base 10. So those are the numbers that you and I use on an every single day basis. Binaries have a base of 2. We are going to get into this into a later chapter in this book, and we're actually going to cover the different number systems. So we're going to talk about octal, hexadecimal, all those different things when we get into it. Okay? But decimal, like I said, it's the numbers you and I use, our counting numbers, things like that. Binary is only 2 numbers, it's base 2, and they are a 0 and a 1. Notice on kilo the difference between when we use an SI prefix, we use a lowercase k for kilo, meaning 1,000, and in binary we use a capital K for kilobytes. Okay, so there's the distinction between our two kilos when we do that. Okay, and there's the distinction between giga. Giga in decimal is 10 to the 9th, right? Or in binary, it's 2 to the 30th when we do that. All right, so let's talk about this. This is us understanding our difference between decimal and binary numbers. So we have a micrometer. 1 micrometer is how much of a meter? Remember, micro is 10 to the minus 6. So we're kind of reviewing what we did in electrical. We have 1 kilogram, all right, equals 1,000 grams. Now that K should be a lowercase k, so a little bit of a glitch on this one. We got 6 megahertz, okay, which should be what? Mega is times 10 to the 6th. All right, so we should have 6 million hertz when we do this. Just so you know, a nibble is 4 bits, a byte is 8 bits, a word is 2 bytes, which is 16 bits, and 6 megabits is 6,291,451 bytes. So go back through and make sure that you got a decent understanding of those. So how many bytes are there in 16 kilobytes? All right, 16 times 10 to the 24th is 16,384 bytes. How many bytes are there in a megabyte? All right, it's 2 to the 20th, so it's 1,048,576. And how many bits are there in 24 kilobytes? All right, so we got to take 24 times 1024. Okay, and then there's 8 bits in a byte, so we have to multiply by 8, so we get 196,608 bits. Not too many test questions or things on that. I don't expect you to necessarily need to know all that to be successful in programming your PLC. Okay? All right. So, just basics, all right, behind where computer programming has come from. All right. So our first generation was machine code. Okay, so what did they use for machine code? Really large rooms full of a computer, and that's what a punch card is. Okay, it just reads the sequence of the holes in the card as it goes through. Same kind of thing, Scantron, if people still use that and you take a test on a Scantron or something like that. Okay, so more of an assembler type language and things like that. Where we went into assembly language, right, when we started using a compiler, so second generation. And then third generation, all right, where we code C++, Java, VB, ladder logic, MATLAB, all these, basic stamp that we use, microprocessor. We can even throw, our Arduino stuff in there, and our Raspberry Pi and Python. All that's more of a third generation type thing. And then fourth generation, you'll use it more in college. LabVIEW. We did use LabVIEW though in digital electronics, right, when we were programming our FPGA boards and things like that. Okay, we also use Quartus to do that, program our FPGA boards as well. So there's where we can program and then upload and execute as well. So multi-sim would fit in that fourth generation stuff as well that we've all used. Alright, so we're going to wrap this up here. What type of memory is volatile and therefore only used for storing variables? Alright, only one answer is correct, and if you answered RAM, you're good. You need to remember that RAM is volatile. Okay. Alright guys, so that's kind of the basic ins and outs of PLC memory, addressing, how we're using the inputs and outputs and that sort of thing for the class. Alright, remember you're going to do some PLC programming at the next level as well. We're going to get you through the basics, understand all of our ANDs, ORs, inverters, XORs, XNORs, NORs, NANDs. We're going to get through all that. We're going to program a stoplight. We're going to program station 1. Alright, so we're going to use counters, timers, those different things. That way you can take it to the next level at level 2. So remember, we're just getting through the basics, understanding the concept of ladder logic in this class, and we will be programming soon. Alright guys, as usual, email me with any questions. Else, have a great day. I will see you in class.